Good evening, everyone, and welcome back to today's last paper presentation session, which session is focused on symmetric cryptography. And for this session, we have as session chair, Dr. Jayaprakash Kar and Dr. Debalina Ghatak with us. For question answer session, there is an announcement. For each paper presentation, after the talk of the presenter, you can keep your question in the QA chat box. And if you have more, which do not permit your time, then you can keep it in the Google Meet link at QA session. Thank you.
Good morning, good afternoon, all of you. Like the other sessions, also these sessions also have the three papers. The first one is proved indefensibility of enveloped Xor revisited. Second paper is sequential indefensibility of confusion diffusion networks. And the third one is that a lightweight implementation of server resistance against side channel attacks. So welcome the first papers, welcome these authors, Risiraj Bhattacharya, Mridul Nandi, and Anik Rai Chaudhary. So requesting you, one of the author, you can come to platforms and can present your paper.
So we've lost Professor Anik Rai Chaudhary. He's just reconnecting. Professor Anik Rai Chaudhary, you may begin your presentation, please. Thank you.
Thanks. So, good evening all. Welcome to this talk titled Proved Indifferentiability of Enveloped Xor Revisited. This is a joint work by Risiraj Bhattacharya, Mridul Nandi, and Anik Rai Chaudhary. So, as we all know, hash functions are very important building blocks of modern cryptology. We use them in various settings, and the usual security criteria of a hash function usually demands pre-image resistance, second pre-image resistance, collision resistance, etc. Now, a popular methodology for designing cryptographic protocols is the random oracle model. At first, we design an ideal system in which all parties have oracle access to a truly random function. And then we replace the random function with a good cryptographic hash function, such as MD5 or SHA-3. In this way, we can basically replace the ideal system in the real world. And Bellare and Rogaway developed this method. Morar et al. Introduced the notion of indifferentiability, which is basically a generalized version of the usual notion of indistinguishability. Suppose small f is a public primitive and we build a construction C using small f as a building block. And then we claim that it has same security as a public primitive capital F. To show this, we basically construct an algorithm capital S, which we call the simulator, which has access to capital F and which tries to mimic F. Now, if any distinguisher having access to small f can distinguish between C and small f and capital F and capital S, then basically we say that capital C and capital F are indifferentiable, and in that case, C can replace capital F in arbitrary constructions. So, this is the indifferentiability game in picture, and this is the formal definition. I will not be going into this. Now, whether we talk about indifferentiability or indistinguishability, one common trait is that none of them, this is assumed that the building blocks or the primitives they themselves are corrupted. To address those issues, Long and Young started the study of cryptography. Informally, cryptography represents the threat of a malicious attacker who, through some backdoor, can implement a defective primitive. Now, basically, what happens is when we implement a hash function, we either get it from some online library or we buy some software. But what is the guarantee that the software we have bought or the code we have gotten from the online library are the actual hash function and they themselves are not corrupted. Now, of course, if the defective hash function differs from the original hash function in very large amount of inputs, it will be easy to catch by randomly checking. So, a common way to model the adversaries in these cases are the so-called curious but proud model. The subverted function differs from the original function only in a small fraction of the points. Now, there have been many studies to address cryptography and related issues. Russell et al. In their Crypto 2018 paper titled Correcting Subverted Random Oracles initiated the study of crooked indifferentiability. Their goal was to use the subverted hash function in a compromised setting. Now we will first describe how the crooked implementer or the adversary in the crooked setting works. So basically what happens is that the adversary in this case has at first advice string to itself. Basically, even before of any phase, the online phase begins, it queries the family of random functions on some fixed number of points and get the input-output pairs, and it uses them as an advice string. Now, after when the online phase begins, when function FL and the input X is given, it decides whether to crook or subvert FL at the point X in the following way. So it has X and FL. So then basically what it does that it queries FLX at some point I. If basically it queries FI at some point Y, and then depending on the, of course, depending on the input X and its output Z, it queries FI at some point I and gets, sorry, FI at some point Z and gets the output W. Then depending on the pairs Y, X, L and IWZ, it decides its next query, and it goes on like this for a fixed number of times, say Q tilde. So basically after that it has a Q tilde many input output pairs to it, and depending on those Q tilde many input output pairs, it decides whether to crook FL at the point X or not. Now, if we want that the function, the subverted function family F tilde L is undetectable by random checking, we will need that for each L, probability FLX not equal to F tilde LX is very small. This is the crooked indifferentiability notion. It varies from the usual indifferentiability notion in the following way, that in this case there is a public random string R which is used to initialize the construction, and in the second phase of the random, the random initial value R will be sampled and given to the construction C and also to the adversary. And in the ideal case, the simulator will get the transcript of the first phase, basically that we talked about, the advice string. It will have access to that. It will have access, black box access to the subverted random oracles and the initial value capital R. So Russell et al. In their paper proved a composition theorem similar to the composition theorem proved by Maurer et al. In their famous paper. They basically say that if C and F are crooked indifferentiable, then we can replace capital F from any construction by C. This is the enveloped Xor. So this is the enveloped, and they introduce the enveloped Xor construction. Informally, the enveloped Xor construction can be described in the following way. Its domain is the integer set 0 to L and its cross product with the bit strings of length n, binary bit strings of length n. And if capital H is all the functions from the domain to 0, 1 to the power n, for every x belonging to 0, 1 to the power n and an initial value capital R, we define grx as the Xor of f1 x plus r1, f2 x plus r2 up to fl x plus rl, and then we apply f0 on it to get our final output. Now, while going through the proof, we discovered some inconsistency there on their proof. They basically proved a very interesting rejection resampling lemma and used that to prove their claim. Now, there were some inconsistencies. Some of them we have listed below. One incompleteness of their proof was that they basically did the proof for a single query. They didn't address the case when the adversary can find two messages M1 and F2 whose capital F values are same. Basically, capital F of M1 equal to capital F of M2. Another inconsistency for handling multiple queries comes in the following way. Basically, they call a function h and a public random string rh unpredictable if for all message m there exists an I such that mi plus r is not crooked for h and mi plus r has not been queried by any crooked point of h. So they then basically argue that if the resampling is done on such an index I, the transcript of the interaction will not change. But this claim is justified for a single message and not for multiple queries. We can basically make batch queries of the type of m and m plus all one strings. And in that case, the adversary can always query m plus one for, basically if the adversary is the subverting algorithm can always query m plus one for m. And in that case, while answering the queries for g of m plus 1, those values will already be previously fixed, and that case has not been addressed. Okay, and the main technical claim of that paper was that if we take the probability over the resampled f function, then g tilde rx, basically the subverted grx value, this belongs to some set is very small because g tilde rx is uniformly distributed under resampling distribution. Now in their case they took E to be the crooked set, but the crooked set of F0. But the problem is the crooked set of F0 can depend on other functions F1 up to FL, because if the subverting algorithm at F0 can query F1 up to FL. So those two, the event E and the G tilde Rx, they are not independent. So we cannot upper bound in that way. So after going through the proof, we tried to correct their proof and we have succeeded in that. We mentioned here that we have communicated the issues with the authors and they have acknowledged them. And since then they have uploaded a revised version in ePrint. Their new version uses techniques like discrete Fourier transformation, while our proof depends on simpler techniques. Okay. So we will present a brief outline of the proof. We use the game playing technique. So there are 4 bad events. The 4 bad events can be described as following. That first bad event is that the input to F0 belongs to the crooked set of F0. That is the obvious bad event. The second bad event is the input to F0 already belongs to the previous input-output pairs or the previous transcript of the input-output pairs. The third bad event is that the input of F0 at some ith query collides with some query at the jth stage. Basically, for some j less than, basically the input has already occurred in the transcript before. And the fourth bad event is that the input of F0 belongs to query set for some x such that x belongs to the crooked set of f and x has already appeared in the transcript. So we bound the individual bad events and then add them to get our result. Informally, we are able to show an security advantage of the order of q tilde q2 square by 2 to the power n plus L q tilde q2 epsilon to the power 1 by 16, where q tilde is the maximum number of queries by the subverting algorithm per query, and q2 are the number of queries to the 2 oracles, and L is the length, basically the 0 to L, that function family from where we sample basically the length of the indexing set. Okay. So basically, we define something called a good point function pair. Informally, a pair YF is good if Y is not a cooked point for F, as well as Y is not queried by a large number of X. And then with appropriate parameters, we are able to show that when we take the probability over Y and F, that the probability YF is not good is very small. It is of the order of epsilon to the power 1/4. Okay. We basically then construct a set of which we call critical values. They consist of pairs, the random string of the public random string R and random functions F, such that for each m there exists an index I, that m plus Ri and F. M plus Ri is good for Fi. That is basically m plus Ri is not a cooked point for Fi, and also m plus Ri has not been queried by any cooked point for F. And we call such a G the critical set. We are able to show that when we take the probability over RF randomly, that for basically R and F both are sampled randomly, they doesn't belong to critical set. That probability is very small. It is of the order of epsilon 1 to the power 1/8 into 2 to the power minus n. So TR subscript J denotes the transcript after J queries. And we call that the transcript after I minus 1 queries is good if the probability that RF is good, given that if agrees up to the with the transcript up to I minus 1 at query, is close to 1. And if we fix K, we say that if is called good, TRI good, basically good with respect to the transcript up to ith query. If agrees with the transcript up to I minus 1 at query, and alpha K F, basically M plus RK comma F is good. Then for any TRI good F, we show the existence of a set which has set S which has size almost 2 to the power n, that is almost the size of the whole domain. And for all beta, if beta is the function that we basically that agrees with F on all points but alpha, where we set F of alpha equal to beta. So for all such F beta, so if is TRI good if there exists a size set S of size almost size 2 to the power n, such that for all beta belongs to it, all beta belongs to S, F beta is also TRI good. So then if we take any event E, we have, when we condition the probability of E given TRI minus 1, we are able to show this lemma that it is less than equal to the summation from K equal to 1 to L, that probability is taken over F here. Probability E given alpha K comma F is TRI minus 1 good, plus some 3Q tilde epsilon 1 to the power 1/16. So then we replace our bad events, bad 1AI, bad 2AI up to bad 2CI with E. And using this lemma, we can get the individual bad events. And after that, we sum them up to get our result. So these are the references. Okay, I have, this is all. So if you have any questions.
Thank you, Dr. Anik. Okay, thank you, Dr. Anik, for this wonderful talk. So any questions from the audience? So I think there is no question from the audience.
I have one question. The link for the Google Meet is the same as you have sent in the Gmail, right? Previous day. For the Q&A session.
I have just shared it on the personal chat for you on the Zoom platform over here. I have sent it to you separately.
Okay, thanks.
Okay, then thank you, Dr. Anik, for your time, and thank you, the audience, for your attention. Thank you very much.
Okay, the second paper is sequential indefensibility of confusion diffusion networks, and the authors are Kui Da, Sanjeev Hu, and Chun Gu. So requesting one of the authors, you come to the platform and can present your paper.
Oh, okay, thanks. Hello, everyone. My name is Chida from Shandong University. Our topic is the sequential indefensibility of confusion diffusion networks. First, let us introduce the definition of substitution permutation network. We call it SPN for short. Concretely, SPN yields an WN-bit block cipher by interrenting the following three steps. The first is key addition by XOR round key with WN-bit state. Second is substitution. It breaks down the WN-bit state into disjoint chunk of n-bit and evaluate a small bit permutation, typically called an S-box on each chunk. The last one is permutation. It applies a big size permutation with simple construction. SPN fits into the confusion diffusion paradigm. The permutation can be viewed as confusion, while the permutation is viewed as diffusion. The idea go back to the festival and even back to Shannon. While various popular primitives have been built upon this, such as the block cipher, like AES and rectangle, and also the hash functions such as the permutation of the SHA. We consider the S-box are independent random permutation, while the D-boxes are fixed explicit nonlinear permutations. Previous work introduced the new model called confusion diffusion network in 2016. It is similar to the SPN, but do not have keys. We can view CDN can be a domain extension maximum for permutations, but here is the question: how many rounds is enough? And next, we introduce the definition called indefensibility. How do we prove CDN can be seen as a permutations? So we use the definition called indefensibility. In this setting, distinguisher D is trying to distinguish between the real world and the ideal world, which means the distinguisher is trying to distinguish the CDN construction from a random permutation. In the real world, distinguisher has Oracle access to the construction CDN, and it also has Oracle access to each individual S-box used in our construction. In the ideal world, the CDN construction is replaced by a real giant random permutation, and to have the same interface in the real world, we need to use a simulator. The simulator has Oracle access to the random permutation, and it has to make up answers to look consistent with the permutation. If we consider the distinguisher is sequential, called sequential indefensibility, we restrict the distinguish order to be primitive constructions sequential. In the first phase, the distinguish query the underlying primitive S-box and the simulator. The number on the arrows represent the order. However, if in the second phase, it queries the construction CDN or the random permutation. In this situation, the distinguisher could not just query this part. However, if we change the order of query, the situation will be different. If the distinguisher first query the construction, then the distinguisher could not query another primitive security model anymore. It could just query this part. Because we restrict the query order of distinguisher, it is weaker than the full indefinability. The sequential indefinability notion has the advantage of being the simpler and easier to use in the proof, but it is still strong to imply the correlation intractability. Though this introduce the model of CDN and establish the probe security in the plan indefinability framework using the nonlinear debox. 5 rounds are proved indefinable. In our work, we first exhibit an attack against the 2-round CDN, which shows the tightness of our positive result on 3 rounds. We prove that the 3-round CDN with nonlinear diffusion layer achieve the notion of sequential indefinability, which is our main result. First, our 2-round CDN constructor is shown in the figure. We need 3 steps as follows. First, we choose n-bit string B, D1, D2 such that the first n-bit output of debox are identical. Second, we query A1, A2 to obtain the A, C1 and C2. Third, we obtain the F1, H1 and F2, H2 by query the oracle P. If P is a 2-round CDN oracle, it is necessary that hold that F1 is equal to F2, which means the distinguisher always put output 1. On the other hand, if P is a random permutation, the probability that distinguisher output 1 is just Q squared divided by 1 by 2 to the power n within Q queries. So the distinguished advantage is that 1. The attack is work. Next, we show our 3-round CDN construction with input and output is both the WN bit. Each S-block is an n-bit permutation. We call n is the wire length and the W is the width of CDN. We use nonlinear diffusion layer in the proof of the 3-round CDN. Apparently, debox input and output size is WN bit because nonlinear debox satisfies certain combinatorial requirement and it is more security than linear debox. We will introduce 2 combinatorial properties of debox. To simplify the expression, we let the input of debox is x1, x2, x3, x4, which means that W is 4. We only focus on one of the input. For any fixed x2, x3, x4, and for any y2 star is and for y2 star is another values in output. There is a low probability that exists the x1 such that y2 is equal to y2 star. Here is another property. X2 prime, x3 prime, and x4 prime is other input. For any x2, x3, x4 not equal to x2 prime, x3 prime, x4 prime, there is a low probability that exists the x1 is equal to x1 prime, such that y2 is equal to y2 star. There is an important sense is how to build the simulator. We use chain complete technique. It requires the simulator to detect particle computation chains formed by the query to the distinguisher and complete the chains in advance. Simulator is ready to answer the queries in the future. To simulate the answers that are consistent with the random permutation, simulator has to use the answer from a permutation to define some simulated answers. This action is called adaptation. In this situation, the work of our simulator is follows. The distinguisher first makes the query X with which is one of the input of the second layer X boxes. The simulator extend x to xb and yb, which extend the length to n to wn. We obtain the xc by yb and xa by xb. Then the simulator query the random permutation to get yc. Finally at the last layer of the Xbox, the simulator makes the adaptation by using xc and yc. If the simulator makes a query y, which is one of the output of the second layer Xbox, it is similar to the situation we talked about. We simplified the previous model. Z is the WN bit random permutation, S is the simulator, P is the small random permutation with n bit. The most important thing is we need to find out the distance between the real world and the ideal world. We need to add an intermediate system. It functions as a bridge between ideal world and the real world. Simulator has both access to Z and P, and the distinguisher can query the simulator or query the CDN construction with Oracle access to S. We first find the distance between the ideal world and the intermediate system. We can see the distinguisher first query the simulator with Oracle access to Z and P, both in ideal world and the intermediate system. If the pair is good, the answer that the distinguisher received are identical. On the other side, Z is an ideal primitive and the CDN is the real structure. So the distance between the real world and the sorry, this is wrong. This is G1 and G2. So the distance between the ideal world and the intermediate system depend on the pair ZP. Next, we find the distance between the real world and the intermediate system. We noticed that the real world only have access to P, so the situation is different. The most important thing is how to get from the pair ZP to P. So we use the random mapping to solve it. We define the map gamma on tuples of random permutation ZP. When the pair is bad, the map is a special symbol. When the pair is good, it will be the tuple of the particle permutation beta. For the tuple of the permutation P in the real world, we said P extend a tuple of particle permutation if for each beta and P agree on all entries. So we can use beta to find out the distance between the intermediate system and the real world. Thereby, we can find out the distance between the real world and the ideal world.
Can hear you,
want
sir.
to know that the attack you have described, it is the classical attack or the public or the sequential attack for the 2 round?
Yeah, I can't understand.
The 2 round attacks for the CDN, is it the public? Is it the sequential adversary or the classical adversary?
It is a sequential adversary.
Okay, I probably didn't understand correctly, but okay, so then that's fine. That's what I think it should be. But anyway, okay, that's fine.
So if there are no more questions, then thanks to the author for this wonderful talk. Thank you so much.
Yeah, thank you.
So the last paper is this session is a lightweight implementation of Cyber resistance against side channel attacks. The authors are Abu Bakr, Kamar Mahajarni, Bhaid Ba Dang, Jens Peter Kaps, and Chris Gach. welcome. One of the authors, you can take the platform and can present your paper.
Hello, do you hear me? Do you see my screen now?
Yes.
Okay, so thank you for the introduction. So this is Abubakar Abdulgadir presenting our work, a lightweight implementation of Sabre resistant against side channel attacks. This is a joint work with Kamir Mohagirani, Vid Dang, Jens Peter Kaps, and Chris Guy from George Mason University. So the development in quantum computing nowadays threatens all our public key infrastructure. So algorithms like RSA, ECC, all of these are vulnerable to attacks from quantum computers. So Sabre is one of the candidates that are believed to resist attacks from quantum and classical computers. And it's basically a key encapsulation mechanism that you can use to exchange keys from between communicating parties securely. It's a lattice-based scheme based on the hardness of modular learning with rounding, and it has been shown so far to be very efficient to mask in software. Basically, if you need to protect it against side channel analysis in software, it was shown already that that will be efficient. So now Sabre is a NIST PQC finalist competing to be the PQC standard to be used for quantum safe encryption or key encapsulation. So in this work, what we do is investigate the effect of applying side channel countermeasures on full hardware implementations. So previous works concentrated on software implementations and software hardware co-design implementations. So in this work here, we concentrate on a full hardware implementation, apply side channel resistance, and see the cost of that protection. So side channel analysis is a well-known threat to the deployment of algorithms, especially in IoT devices, where you have the adversary having access to measure power or measure also electromagnetic radiation or timing, and that will threaten successful deployment of these systems. So basically in any cryptographic system, you have your main channel. For example, you feed it and you feed your device plain text and you get out ciphertext. This is the main channel, but you also have side channels like timing, power consumption, electromagnetic radiation. And by measuring these side channels, the adversary can learn information about the sensitive information, such as the key, and break the whole encryption system. So for this reason, you need countermeasures to resist these kinds of attacks. The problem with countermeasures are that they're costly. For example, in hardware, they can increase the area, and they can also make your device performance also reduced, and that's algorithm dependent. So for each algorithm, you need to do a careful study on that algorithm to see what's the effect of adding side channel countermeasures. So we did this study on the Sabre algorithm. The countermeasure that we are interested in this work, it will be masking. And basically the idea of masking is that you have your sensitive data and then you split it into shares. You compute on those shares securely and make sure that you're doing the computation correctly and at the same time not leaking any information about the secret that you're trying to hide. One of the types of sharing is Boolean masking. Basically, you split your sensitive data into shares such that when you XOR these shares, you get the sensitive value. And there is this arithmetic sharing. When you add the shares, you get the sensitive value. So these are one of the two. These are the two most common types of masking that you can use. And also, depending on the platform itself, you need to make sure that you're applying the correct countermeasures. So, for example, in hardware, there is a phenomenon called glitches. Basically, these are temporary changes in the signal before they stabilize at the end of the clock cycle. So these glitches can cause some leakage. And there are some countermeasures that are suitable for hardware. For example, threshold implementation and domain-oriented masking. These are types of countermeasures that are designed to resist glitches. In general, in any masking scheme, linear operations are trivially masked, but nonlinear operations need much more work. So our methodology to do our work on Sabre was to start first from a baseline lightweight design, and basically that will give us two benefits. First, in the protected design that will build on top of this will be some of the components will be used as is. So for example, polynomial arithmetic and many other functions will be used as is. So that will give us this reusability of resources. And the second is that since we are building on this baseline design, we can directly compare these two designs. So we have a meaning comparison on the cost of adding countermeasures on this design. So the design that we built uses the transfer level, register transfer level methodology, and we coded we described it using VHDL and Chisel language. This design uses a flexible polynomial multiplier based on schoolbook methodology, and it's very flexible. And also we have a very flexible SHA-3 unit. So these are the two main operations, the most resource consuming operations in our design. So having them configurable makes the whole design very flexible. So in general, we store everything here in this memory, in this RAM, and we feed the data into the polynomial arithmetic units, and the data goes back into memory. So basically, before you feed it into the polynomial arithmetic units, you go through these width converters, which are responsible for changing the byte strings stored in the memory to coefficients that will be fed into the polynomial arithmetic units. And then you pack these polynomial coefficients into byte strings back using this width converters. You also have the 3 unit and sampling units that are also used. So here are some of the major units that we use in design. So for example, has a polynomial multiplier, and the flexibility comes from set the numbers, the number of the multiplication units that we instantiate inside of it like this, and that will give us area performance trade-off. We have also the sampler, which is responsible for getting the binomial samples, and it receives its input as uniform samples, and then it will calculate from those samples the binomial samples. We have also the width converters that I just discussed, and it's responsible for packing and unpacking polynomials from memory. So Mask Sabre was already discussed in software, studied in software, and this data flow diagram from Berendonk and others shows how you can process shares securely in Sabre. So the idea of this data flow is that you split your secret key, your private key, into 2 shares additively, such that when you add the 2 shares, you get your original private key. The private key is the most sensitive resource in Sabre because it's used long term and it's used in the decapsulation algorithm. So the attackers will be after this key, the private key. So the idea is that you split it into shares and then you compute on these shares securely. The main challenge here in Sabre is that some of the operations like SHA-3 favors Boolean masking, some operations favor arithmetic masking. Some of the operations, for example, that do polynomial arithmetic favors arithmetic masking. So you need to securely do this conversion between arithmetic and Boolean masking. So for our design, we chose to duplicate all the linear logic and redesigned all the nonlinear components. So this is how our Mask Sabre design in hardware looks like. And if you notice that it looks like 2 copies of the unprotected data path in the right and the left, these can process 1 share securely, and you don't have to mix the shares. However, we have these units labeled in highlighted in red here in the middle. All of these units have nonlinear operations inside of them. So in nonlinear operations, you need to mix the shares. So in that case, you need to be very careful and mix them in such a way that you don't leak any information. So what happens here in this design is that data comes from the memories on the right and the left, go through the polynomial arithmetic units, and then through the nonlinear units where you have to mix the shares, and eventually each nonlinear unit will output two shares that we can securely merge back into the respective parts of the data. So here I'll briefly discuss some of the major units we used in the masked hardware. So for example, this is the logic shift unit. So in the compression is done by bits on the polynomial coefficients. So basically, this operation is free in unprotected hardware because you just discard the bits. In the protected implementation, it's more difficult because you receive arithmetic shares, and the logic shifting is a Boolean operation. So the idea of this, which is taken from the work by Brendonk and others, we did the hardware implementation for that algorithm. The idea of it is that it receives arithmetic shares, do the shifting, and eventually output arithmetic shares that are can be usable for the polynomial arithmetic units. This is a sampler that we used in our design based on an algorithm by Schneider and others. And basically what it does is receiving uniform samples and output binomial samples, and it takes one bit at a time from each input of uniform samples, do a conversion to arithmetic sharing, and accumulate those until you get your binomial sample. This is how our SHA-3 unit looks like. And basically, this is a very configurable SHA-3 unit. It can do SHA-3 256, SHA-3 512, and Shake 128. And it has a very flexible design. It can do we can do a performance area trade-off, and basically that's done by configuring the number of slices that we can process every clock cycle. Domain-oriented masking was used to protect this design. So here I'll briefly discuss the results. So to assess the security of our design, we performed leakage assessment using the test vector leakage assessment methodology. And on the top, you see the graph on our protected implementation, while the random number generator is disabled, the PRNG is disabled. So once you disable the PRNG, you're basically disabling the countermeasures that you're using. And we can clearly see that there is a leakage that shows that, and this is how what we expect. And this also shows that our setup is able to distinguish leakages. The second graph on the bottom, we enable the PRNG, enabling all the countermeasures that we have, and clearly we can see the t value within the threshold, and that one spike at the far right is when we compare the ciphertext against the re-encrypted ciphertext, and that should not give the adversary any advantage. So here is a comparison of our work with previous works. There are two implementations of masked Saber, one running on ARM Cortex M4, and one is accelerators on a RISC-V implementation. So this shows that our design, compared to the baseline design, we got from this number of LUTs to this number of LUTs. Basically, what happened is that it's almost 3 times the LUTs because we duplicated the data path, and there are some units that grows in a non-linear fashion. The DSP units also has been doubled, and we can see that the latency is around 1.36 times. So this summarizes the cost of protection in our design. So the LUTs grows by 2.9 times, DSPs grows by 2 times, and the latency by 1.5 times. Here is a breakdown of the major units that we have in our design. And basically from this diagram, we can see that the polynomial arithmetic, the polynomial multiplier, SHA-3, and the main memory take most of the area. But when we go to the protected design, we can see the protected design below here. We can see that the sampler, the central binomial sampler, is also very significant in area. So to conclude, the cost of protection in our design was 2.9 times the LUTs, 2 times the DSP units, and 1.4 times the latency. Our protected design is also 29 times faster than previous NAS software running on ARM Cortex-M4, and 26 times faster than the software hardware co-design based on RISC-V that was reported previously in literature. We can clearly see that to improve these results, we need to concentrate on the polynomial arithmetic unit and the SHA-3 unit for both the unprotected and protected designs. But also in the protected design, the CBD sampler is also significant. So reducing the size of that and improving its performance will be useful. So for future work, we suggest focusing on fault attacks and deep learning based attacks, and also further reduction in resource utilization and performance improvements can be achieved. Thank you for listening.
Thank you very much for this wonderful talk. So any questions from the audience? And so can I ask one question? Yeah.
Sure.
So you have used SHA-3 in your design, and you mentioned that similar kind of designs can be made with SHA-256 or 512. So have you tried, is there any drawback in those SHA functions? That was my question.
No. Yeah, so in Sabre, what we do is inside the algorithm, it needs to use SHA-3, 256, 512, and Shake 128. So all of these sub-functions of SHA are used in Sabre. So our design is flexible. So it's a SHA-3 unit, but it can do all of the 3 functions, and all of them are actually needed in Sabre.
So any SHA function can be used for the same design?
We need SHA-3, but specifically SHA-3, 256, 512, and Shake 128. So all of these functions will be called, all of those will be needed. So you cannot use one and discard the others. The algorithm will call each of these individually.
Okay, thank you so much. So
Thanks.
any more questions from of somebody online?
So there is no any questions in this chat box also. So anyone in this physically in the venue who might be any questions, they can ask. Here there is no any questions in the chat box.
So I think there is no question from the audience here. So let us thank the author again. Thank you.
So thank you all. Thank you to the authors who have presented their paper so nicely. And thanks to the session chair, Dr. Kaur and Dr. Ghatak, for being there. So now we'll be having a 15 minutes break, and then the Indocrypt 2021 RAM session will be beginning at 7:45 p.m. sharp. Thank you.